Hello children, a very warm welcome. Today we will be starting with the initial chapter of the book and the whole unit, that is force. Now of the full unit, force, work, energy, power, we will be dealing with chapter 1 right now. The term force is already known to you because you have studied it in the previous class, Newton's laws of motion and the types of forces and everything. In this class and in this chapter particularly, we will be dealing with only one type of body, that is rigid body. Rigid bodies, for example, happy to see, especially those who plays cricket. Now, if I put any kind of force on it, a light force, okay, now something more, is this ball changing its size or shape or getting discolored or something like that? I suppose it's intact, as you can see. So this is an example of rigid body. Now coming to the effect of force on this. Observe clearly, as I am giving it a force, since this body is a rigid one, its mass is constant. There is no change in that. Its volume is also constant. So, if I apply force, what exactly is changing? It started moving. Let's try one more experiment. This type of things you must have played with when you were a child. So this is one of my childhood toys, which is a broken car. So as you can see, it's fully made of plastic, and this one are certain metal rods attached. So as much as possible, whatever force or I am applying, there is no change. So this is also a rigid body. In that case, if I am applying force, there is a displacement, change of position, body is accelerating, various terms can be applied. That means initially when the body was at rest, as you have learnt about the Newton's laws, that until and unless a force is being or an external force is being applied, there is no change in displacement. And whenever an external force is applied, there is a displacement. That conclusion, there is a motion produced. So, we will be dealing with different types of motion. For example, if I talk about this toy car representing any vehicle, of course, when there is an external force, since this is a toy car, I am able to give an external force and it is getting displaced. For the regular vehicles or the bus, car, trains, for an example, there is an engine fitted inside, and whenever the key is moved, it is switched on, the engine starts supplying an energy and it causes a displacement. And finally, we can see a motion. Now, whatever motion I have displayed, maybe with this or maybe with this, are all of the motions same type? There can be different types of motions. So in that case, let me show you another one. Hopefully, you could easily see that there was a fan which was moving. Okay, I agree, there is no displacement caused, but is the fan exactly steady or constant at its position and there is no motion, there is no movement which you can see. The blades are getting displaced to be very particular. If the blades are constant, I'm showing you a different one which is really constant one because I have kept it switched off. So in this case, it is a different one for which I have kept it switched off. So you can see that the blades are not moving. But in case of the ceiling fan which was switched on, you could easily see that the blades were getting displaced, but the whole of the body of the fan was not getting displaced. So let's come to the, I hope you all have the textbooks in front of you. So I would really request you to open the first page of the book and let's study the moment of force under the heading and the translational and rotational motion. These are the different types of motion. I am coming to them one by one. First, let me tell you about this. That is this one. In this case, I can follow many types of motion. First of all, when I am pushing it forcefully, you can see that the whole of the mass is getting displaced in a particular direction. Might be this, might be this, or if I leave it and give a motion, it will start accelerating on its own, and then also it will just go in one direction, or it will accelerate in one direction. This type of unidirectional motions are known as translatory motions. One more example. Another car. Yes. So if I again give it a force, it will just go on moving in one direction. All these are happening because of a push from one side. As you can see the diagram 1.1 from in your book, the force is drawn from one direction. The body is getting displaced in the same direction. It is shown as direction of motion. Coming to the second type. In this car, what can be the parts you can see? Number one, the full body which I am holding. Number two, there are 4 wheels which are pivoted at certain points and they are fixed to this car body. Sometimes when we check it, what do we do? Is the car getting displaced in this case? No. But the wheels are only showing the motion, keeping itself fixed at one particular point, and the rest of the body is rotating about its mean position. Why I am telling mean position? Because it's rotating about the pivot point around a certain axis. A greater example or something I have brought, I'm going to get scolded because I have taken it from the kitchen. Shh. See, here you can clearly see a pivot point that is at the center. Here is a screw attached which is symbolizing the pivoted point, and over here you can see the place where I am holding it. So the body is actually taking the motion around this pivoted axis. So this type of motion where the body is rotating around a certain pivoted point or around a certain axis, like for example of the wheels of this car, a very good childhood poem we remember. I suppose you have read it too. Wheels of the buses go round and round, like that. So this is the wheels of the car which is going round and round. All these are the examples of rotational motion. In this case, all the points of this dish is getting displaced. From here, if I see, it is getting 180-degree displacement, exactly opposite. Or if I hold this is also getting displaced. But all these are happening exactly around one single center point, that is this pivoted point. So I suppose right now the example of translation motion and rotational motion is clear to you, and we will be proceeding forward to our next very vital topic, that is moment. Please turn to page number 2. You are going to see a certain diagram given in figure 1.3 and the heading given as moment of force. What is moment? This turning effect, if I am rotating it like this, it's moving with a certain speed. Now if I am rotating like this, moving with another speed or maybe an increased speed. So a cycle which can travel, for example, 10 km per hour, 20 km per hour, like that, according to your wish, because you are riding it, does the motion of the cycle's wheel be same as that of the motion of the car's wheel or any other faster transport like bus? So this type of different motions, that is the difference in the speed and the acceleration and the effect, how does it causes is signified in this term or under this term, that is moment. So as I showed you about this axis, so let me show you one more thing. How I am giving the force, it is dependent on a basic factor. If I apply a force here, you can see the groove over here, and this is the full radius of the structure. I am applying the force at somewhat less than that of the radius. My fingers over here, they are the same. Of course, I am the same because I am continuing. So the force which I could apply this much. Force is applied in this point and the motion happened over here. So this will be the distance around which the force is being acted. Since I am applying the force over here, so I am not going to consider whatever the size of the body be. I will consider only this much of the distance. You can clearly see the diagram. I suppose in the figure 1.3 it is given, the force and the distance. Now if I apply this same force over here, then the distance is increasing. In fact, with the ruler also, I can show you easily. See over here. Sorry. Now probably you can see this part is at a lesser distance than the full of the plate. So, at what point we apply the force is important. See the factors written in your book. I am reading it out one by one. Factors affecting the turning of a body. The turning effect of a force on a body depends on following two factors: the magnitude of the force, that is the pressure given by my hands, and the perpendicular distance. Every time we should be only considering the perpendicular distance. Now, while studying any type of circular body in detail, when we are trying to measure a particular radius at any time, we have to take the distance perpendicularly. If we hold it like this, which is not exactly perpendicular from the center or not even touching it, we can't measure the point. So every time when we are holding it, we have to hold it center and we have to check whether it is perpendicular from the central point or not, and then we can take the distance. So here, as you can see, I applied the force exactly at 2 inches from the center when I am applying it in the groove, and when I am holding it, you could see it's 3 inches. Magnitude increase, decrease. So these are the two factors which is being demonstrated till now. So as per the definition goes, I repeatedly tell you every time, kindly follow the exact definition of the book. Exact definition does mean that you have to mention the correct physics terms applied. For example, here I am reading it out. Kindly underline the mentioned parts. The moment of force or torque. Question can come like define torque also. Please don't say that it is not in the book, it is written in the bracket. So if you have a tendency to miss, you can underline it and please learn the spelling also. If the spelling of the particular term is wrong, your marks will be deducted. So please go along this. The moment of force or torque is equal to the product of, not the product of force, product of the magnitude of the force. Underline this whole magnitude of the force, and the perpendicular distance of the line. Underline this perpendicular distance of the line of action of the force from the axis of rotation. That is the pivoted point in the case of this dish. So this full definition will be required. Mathematically, as you can see, it's written force, the perpendicular distance is denoted by OP over here. Of course, whenever you draw, if you write AB, of course that will be acceptable. So please don't ask about the particulars of the variables. That's according to your wish, but you have to do the diagram and show it in this case that you are using this. Units. Units of force, as Isaac Newton devised already, and you are knowing it from the previous class. Units of force, it is Newton, that is the SI unit I am talking about, and the SI unit of distance will be meter. So it will be Newton meter together. There in blue lines, those whatever it is written, that is 1 Newton meter is equal to 989 centimeter. This full derivation is important, so kindly mark it and do practice it. See, there is no point of learning or rote memory over here, because 9.8 is a very known value in the case of gravity, motion, acceleration and everything. So 1 kgf is equal to 9.8 Newton, and you will not consider it as 10 until and unless mentioned in any of the numericals. Please children, 9.8 is the standard value. You have to solve all the numericals with this 9.8 value only. So from the initial stage, please start doing that without using, since you are at home, you are getting the facility of calculator or mobiles. Please don't do that, because in the final exam time, whatever changes may be coming, but the class 10 will not be allowed to use any kind of gadgets or devices. Number 2, 9.8 value will be the generalized value as taken, and please don't just use 10 in its place and continue doing that. Okay, so in this case, there are few more things to discuss and just go through clearly. Clockwise and anti-clockwise moment. Clock. A motion of clock is already seen by you, because many a time you are having clocks. My room has got one, but it will, since it's at the top, I can't show it right now. Of course I can show it the next time I will for an example, but with this same thing only I can just explain to you what is to be done. Number 1, clockwise, anti-clockwise moments. See, these are particular conventions taken. Don't ask why positive, why negative. Why positive? Because we have to start certain calculations at one place. So there is always a 1, 2, 3 like that in the initial point. Don't ask, Miss, why is 0 not here? Because we need to start the measurements from a certain point. Similarly, by convention also, this one, there will be certain rules given. When I talk about the anti-clockwise moment, which is given in your book as first one, it is somewhat like this. I can see it moving clockwise. I suppose since you are exactly opposite to me as the mirror image, I think you remember the mirror image. So this is the anti-clockwise movement for you. This movement will be considered positive. You can see the diagram 1.4. In fact, this will be a homework for you also. If you use compass, it will be better. Else, you can use any type of circular thing to draw. Don't draw it freehand just like that. The circumference should be smooth, and the radius of the circular structure everywhere should be same. The anti-clockwise is always considered positive. So in this case, as the diagram is drawn, I am showing it simply that way. That is the force which is given from below, and you are making the rotation in this side. So this side is positive. Is it till now clear to you? Then show me, let me show the another one, that is the clockwise movement. From my side, when I am rotating it anti-clockwise, you are seeing it to move in clockwise, and this will be negative. That you can easily remember clock negative, so that you can remember that anti-clockwise positive, Or since anti-clockwise A comes first, positive, C comes later, negative, whatever convention you use according to you, just remember anti-clockwise to be positive and clockwise to be negative. That's it. That is the final conclusion. How can the direction of motion of a body be changed? Car is going this way. Rotate it, coming this way. Or, as you have seen in the demo, I was applying force this side. The application of force is this side. So, the direction of application of force can be changed. It is in point number 2 of your book. Now, by changing the point of application, I am applying the force from same side. See, that is from here. Your right to left. My right to left. Sorry. My right to left. This thing I am applying. That is the force I am applying. So, what can be the motion? You can see it very easily. Yes, this is anti-clockwise. Now, again I am applying the same force but at a different point. Is the motion same? I suppose no. The direction of the movement of the body changed. So, by changing the point of application, of course, I can change the direction of motion of the body from clockwise till anti-clockwise or from anti-clockwise to clockwise. Okay. Now, some common examples of moment of force. When I talk about some common examples, you can illustrate the example as per as your wish. I just give one suggestion every time because it comes very clear when the teachers check or especially the board examiners check. Do the diagram. After that, in fact, if the diagram is clear, the labeling is clear, you don't need to write 1 or 2 paragraphs explaining that. It's up to your wish. No one can exactly instruct you how to write the question of explanation or example. If you are comfortable in writing, very good. I, as a particular student of class 10, I was never comfortable in writing 1 or 2 paragraphs. I used to draw the diagrams and in the conclusion, I used to write 1 or 2 lines. Let me show you one example of this moment of force. Over here, it is said about hinges of the door. I can go towards the door right now, but I have the same structure, that is of hinges. See this table. A part of the table is folded. As I am applying, you can see the movement of force is acting over here, and this is the axis of rotation. My hand is clear over here, and in this point when I am applying the force, this part of the table is getting displaced. But when I am applying the same force over here, it is really difficult for me to lift it up fully because at that time the total moment is decreased as the application point from the total distance of the force is decreased rather than the full size over here or the full radius considered over here. So, this is one good example. Other examples illustrated in the book is that of the steering wheel. This we always continue to play holding the plates and anything. while the steering wheel shown. So that also can be considered as an example.